Hello and welcome. We are solving few electrostatics problem at the very much start, and the problem at hand is two positive charges Q1 and Q2 are fixed at a distance d from each other, and an inextensible non-conducting thread of length L is attached to the charges. That means this should be the thread whose whole length is perhaps L. A small positively charged ring is here that can slide along the thread without friction. The system is in equilibrium. Find the distances R1 and R2 in the equilibrium position. We don't know the charge on the ring. Perhaps that will not be needed to solve this problem, but we should try. The thing is, these two charged particles are fixed, and the ring slides along the thread on a path. And what can be trajectory of the ring? This is the problem, and I think the curve depicted by the dotted line in this figure is part of an ellipse with foci at the position of charges Q1 and Q2. Yeah, therefore the problem could not be solved using the non-geometrical properties of ellipse, and this is not the problem of reflection, in which we can use that if a ray leaving one focus of the ellipse after reflection from the surface of the ellipse passes through the other focus, this is not gonna to be used here. So we need to go another way. Given in this problem that R1 and R2 are the distances from the ring to the charges Q1 and Q2. So, and the total length of the thread being L, capital L. So I can write one thing here: R1 plus R2 is equal to L, and its thread is an inextensible, so L going to be constant. Yeah, and we know that in the equilibrium position, that means the system is in equilibrium. That means its potential energy is minimum, and that is equal to 0 because all charges are positive. So yeah, I can assume all the charges being positive, because we don't know about Q1 and Q2, and they don't need their, since they are fixed, so that doesn't matter. And the charge on, suppose the charge on the ring is Q, then Q must be positive, otherwise it could not happen. Must have been same sign. Charges should have been same sign. So same sign. So the minimum potential energy of the system will be equal to 0, nothing else. And now I'm willing to use a technique in which suppose the ring has been displaced from the equilibrium position, then what will happen? Very small shift. That means I'm considering an infinitesimal shift of the ring from its equilibrium position, and this shift can be written simply as dr1 plus dr2, and that will be equal to 0 since L is constant. That means dr1 will be equal to minus dr2, and let's call it dr, so that in future I can write dr1 equals dr and dr2 equals minus dr. Yeah, I can call in future like this. And we know the forces acting between them, and for the small displacement I can use this relation between force and potential energy, that is F equals negative of gradient of potential energy, and so that I can write du1 equals force F1, force on charge by Q1 on Q1 on the ring, and that is minus Q1 divided by R1 square. This is the force multiplied by dr, can be written as the potential energy, a small change in potential energy of the pair of charges Q and Q1, and in the similar manner potential energy of the pair of charges Q2 can be written as minus Q2 divided by R2 square dr. This is basically dr1 and this is basically dr2, because here is the change in here is the distance r1, so I can write dr1, and in the second case the distance between them is r2, so the small displacement in r2 can be represented as dr2, and we can write the change in potential energy of the system can be written as minus kq1 upon r square. dr1 can, I should write it like dr and plus dut, and minus dr2 is dr here, so I can write it plus kq2 by r2 square dr. Simply minus dr2 I wrote dr. So the change in infinitesimal potential energy becomes kq dr multiplied by 1 by q1 by r1 square minus plus q2 by r2 square. This was r2 square. Yeah, so this is the small infinitesimal change in the system after we deviate or infinitesimally shift the ring from its equilibrium position. And for equilibrium, du must be equal to 0, and if this is it, I can write one thing here, that is q1 upon r1 square is equal to q2 upon r2 square, and this is our relation 2, and our relation 1 was simply this, that is r1 plus r2 equal to L. Using both these equations together, we can find the value of r1 and r2. R1 will be simply under root q1 by under root q1 plus under root q2L, and r2 you will get under root q2 by under root q1 plus under root q2 multiplied by L, and this is one of the standard results. These distances do not depend on the distance between the charges q1 and q2, so D was an extra information given in the problem. And thank you very much for watching. However, well, thanks.